Welcome. Let's solve Leetcode 684 redundant connection. Okay, so let's read this here or part of it. So, in essence, they want us to return an edge that can be removed so that the resulting graph is a tree of n nodes. If there are multiple answers, return the answer that occurs last in the input. So for this first example, we have these nodes and these edges, and they tell us that the answer is 2, 3. Okay, and here's another example here with, what is this, 5 nodes, and here are the connecting edges. And the last edge that is redundant is this 1, 4, which is given here. Okay, the problem description seems simple enough, or at least straightforward. What we'll be using is something called union find. Other books, or it's also known as disjoint set. So these are two names, but I'll go by the name union find. Okay, so let's go over this. Maybe even this first example. So let's just copy this here. Let's make this a little bit bigger and maybe close this. Okay. So we're given 3 nodes. So let's just draw them maybe here, node 1, node 2, and maybe your node, well, let's put here maybe node 3. Okay. So remember what they're asking us, or asking of us. They're asking us return an edge that can be removed so that the resulting graph is a tree. So a tree, a tree is an undirected graph that is connected and has no cycles. Okay, so notice in this first example, this graph has a cycle. Okay, so they're asking us to find the edge that can be removed so that there is no cycle. And if there's multiple answers, return the answer that occurs last in the input. Okay, so this is the input. So with this first edge, that means that we should connect 1 to 2. So let's do that. We'll just connect 1 to 2. Okay. Now let's move on to the next edge, 1 to 3. So we can add an edge here and an edge here. So now 1 is connected to 3. At this point, we have a tree. So that means this last edge would be redundant. So how we'll be using union find is we'll say this, we'll loop through our edges and attempt to union the nodes. If the union of the nodes fails, we will return that edge. Okay, so how will we determine if the union of nodes is successful or is a failure? So we'll be using what's called we'll keep track of a parent, and then if those nodes already have the same parent, then that's a failure. If they do not have the same parent, then that will be a success. Okay, so let me start implementing the problem and or implementing our solution, and I'll go back to our diagram as needed. So first off, what we're going to do is we're going to loop through our edges. So we're going to say for u, v in edges. And we're going to attempt to union them. So we're going to say, so if we have a failure, we're going to say if not union these edges, then we will return that edge. Okay. And let's check something else. Are we guaranteed that there's going to be there are no repeated edges? The graph is connected. All right, so we should always have an answer. So this should be fine. Okay. Now, if you notice, they tell us that the edges are numbered from 1 to 2, 2 to 3. In order to make it convenient, I'm going to subtract the node values so that instead of from 1 to 5, we'll have nodes labeled from 0 to 4. Okay, so let's do that here. So I'm going to change this to u minus 1 and v minus 1. But as far as the answer is concerned, we'll leave it as is. Okay, so now let's go over what union means. Okay, so what does union mean? We're going to try to connect them. So we're going to say define union. So union will accept two nodes. And what we'll want to do is we'll want to check if these nodes have the same parent. So first, let's find their parents. So let's say maybe the parent of u and the parent of v. So we'll say equals, so find u and find v. So this method here finds the parent of the given node. So initially, what we'll do is we'll say, okay, one will be its own. So remember previously or originally, we had something like this. So what we'll do is we'll say, originally, each node will be its own parent. So let's do that. Each node will be its own parent. So we'll say parent equals I for I in range n. And this will be the number of nodes. Well, we don't exactly know the number of nodes, but we can figure that out. N equals the length of edges. And they tell us that n is the number of edges. So the graph is represented as an array edges of length n, and n is the number of nodes, a tree with n nodes. So we know that. So we have that here. So n is the length of edges is n, and just to go on to maybe talk about that a little bit more is like, notice how we have 3 edges here and we have 3 nodes. So there's a relationship between what they give us as far as the number of edges and the number of nodes. Okay, so now moving back, so now we know the parents. So let's print that out for a moment. So let's print out our parent, just so we can get a look at it. And maybe we'll comment this out for now. And we'll just return maybe edges 0. So I just want us to get a look at what parents looks like. So originally, the first node will be, each node will be its own parent. So in this case, node 0 at index, so index 0 has a parent of 0. Index 1 has a parent of 1. Index 2 has a parent of 2. So basically, each node is a parent of itself. Okay. And now, once we union them, we'll change who is a parent of who. Okay, so then we're going to add a little bit of an optimization here. So I'm going to call this rank, or maybe, yeah, sure, we'll call this rank equals, maybe even size. I would just call this size. Size equals 1 times n. So this means that, so notice here how each node has a size of itself, so a size 1. So that's why I've done this here. I've initialized an array of size n, which would be size 3 in this case. Sorry. And 1 for each value to indicate that the current size of each node is 1, representing itself. Okay. So then now, so let's just assume that this find method has been already written so far. So what we're going to do is we're going to check, okay, if the parent of u is the same as the parent of v, then we return false. So let's go back to this example here. So for this first edge, if we have 1, 2, we'll ask, do 1 and 2 have the same parent? Now remember, initially they don't. They're parents of themselves initially. But after we union them, we'll have to pick which node is a parent of each other. So it really doesn't matter. So at this point, remember, just suppose that something like 1 is a parent of 1, 2 is a parent of 2, 3 is a parent of 3, initially. But once we union them, we'll have to decide which node is the parent. It really doesn't matter. So let's just say now the parent of 1 is 1, and the parent of 2 is 1. Okay? Good. Okay, but originally though, so once we pass in 1 and 2, since they had different parents, we would get past this point because they had different parents. Now let's make them have the same parent. So what we'll do is we'll do a couple of things. We'll say if the size of P is greater than the size of Q, then we'll say we'll do a couple things. We'll say the parent of Q equals P, and then we'll add the size of P. We'll add that. We'll add the values of Q. So size of Q. So let's see what happens here. I want to give a disclaimer though. You should already kind of be familiar with this data structure and this approach. So that's why I'm not going from the very beginning. I'm going a little bit over, but not as much. If you'd like a dedicated video solely to union find disjoint set, then please let me know in the comments. But at this point, I'm assuming or hoping that you've seen it a little bit before and you're vaguely familiar with it. Okay, so remember in this case, each node has a size of 1. But once we change the parent of node 2 to 1, now we're going to say, okay, node 1 has those nodes now. So now this will be, node 1 will have a size of 2 to indicate that 2 nodes are represented by this parent. Okay, and else, so what we're going to do is, if size of P is not bigger than Q, then we'll just do the opposite. So I'm just going to copy this and switch it around a little bit. So that means the parent of P now is Q. And we'll add the node size in reverse. And after that, we'll return true because we've unioned them. So what we'll do here is, I'm actually going to do something here. I'm going to say, let's print this along the way. So what we'll do is this. We'll say, let's say print, let me see, print parent. And then we'll print the size. Okay. And then let's, I think that'll be okay. So we print it, let's print it up. It's fine. Originally, that's fine. All right, let's just try this, see what we get. Oh, that would fail because we haven't implemented this find method yet. Okay, let's do that. So define find. So we want to know how to find the parent of a node. So let's pass in a node here. So we're going to use something called path compression here. Path compression. That makes our algorithm a little bit faster. So what we'll do is we'll say, okay, we'll say node equals the parent of node. And then we're going to keep trying to find our node until we're going to use recursion to keep attempting to find the parent of the node. So we're going to say while node is not equal to the parent of node. Okay, so this next line is the path compression. So it's going to say parent of node equals the parent of the parent of node. And then we'll assign node to the parent of the node. So we'll say node equals parent of node. So in its most simplistic manner, let me explain what's going on here. So let's take the case of this 1 and 2. So remember, maybe make this bigger. Maybe I can make this bigger. Okay. So suppose we pass in 2. And so we pass in 2 to this find function. So the node 2. So in this case, ignore this line here. So the parent of 2 is 1. So node 2, so this would have this here. This would be 2 is not equal to 1. So that means it would continue on. So, or enter the while block. And kind of ignore this too. But notice though how the parent of 2 is 1. So then we go back up here. So then we ask, is 1, well, the parent of 1 is 1. So in that case, it would break. These, especially this line of code here is meant to compress it. So what I mean by that is, again, I didn't plan on going over like in depth, but I'll just go over this one tidbit here, which I think is important. This joint union is a very powerful algorithm or data structure. So let's go over them. So path compression. So what's happening there is this. Suppose 1 is a parent of 2. I'm gonna put it like 1 is. Let me see. 1 is a parent of 1, or let's. How do I do this? Let me see. 2 is a parent of maybe 3. Let's see, 1 and 3. There we go. 3, 2, 4, 3. Okay, here we go. So suppose we have this setup here where the parent of 4 is 3, the parent of 3 is 2, the parent of 2 is 1, the parent of 1 is 1. So suppose what we can do though is saying, so we have this kind of chain here. So 4, something like this here. So what path compression does, it says, even though 3 is the direct parent of 4, the ultimate parent is 1. So what we're doing there is we're saying, okay, we're going to say we're trying to wipe these out. So see how we have to travel this chain? So 1, 2, 3, 4. Wouldn't it be better if we can just kind of wipe it out? These middle layers and kind of just know the ultimate parent of 4, which is 1. So that's what's going on here. That's what we're doing. We're kind of wiping out the middle nodes, so that when we attempt to search for the parent of this node again, it becomes quicker. Okay, I hope that makes sense. Okay, okay, good. And now where are we? So okay, this is path compression. Okay, so this is the method to find the parent, and I think everything else is complete. Okay, so let's run this locally or test it. Okay, let's see what happened here. What is wrong? Oh, sorry. Okay, so let's see what happened here in this case. So for this problem, we have these 3 edges. So originally, each node is a parent of itself. Remember, we subtracted the node values just to, it makes it easy for us. And then each node has a size of 1 to represent themselves. After the first edge, which is 1, 2, okay, we say the parent is, that's interesting, 0, yeah, that's fine. So that's interesting. Why didn't, so 0, so the parent, oh, here we go. Yeah, no, that's right. I apologize. So originally the parent of node 0 was itself, but now the way we set it up was that now this node, now this second node, or this the node at index 1 is the parent of node at index 0. Okay, good. And notice how we change the size of this node to 2. And then we move on. And this would be after the second node. So now, so this is here. So now node 3 also has a parent of 1. So all nodes have a parent of 1. And node has a size 3 because it represents all 3 of those nodes. And then at that point, though, we don't loop again because we return. Okay. One thing though I need to do is I need to change this to, yeah, okay, we don't need this anymore. We didn't need that line. That was just for our testing purposes. Okay, and I think that's about it. We don't need any more. Let's submit it. Okay, great. Looks like we did really good. Okay, so I think part of the reason why our algorithm or our solution is fast is because we used path compression and union by size and rank. So we also did a small optimization here, and these are pretty standard for union find. Okay, great. If you found this video helpful or educational, please consider liking or subscribing, or both. Other than that, have a wonderful day. Take care of yourself. Cheers.